Hi, I'm Bob Stern. I'm professor of geosciences at the University of Texas at Dallas, and I want to talk to you about one of my favorite meteorites. They're called pallasites, and I consider them to be the beauty queens of meteorites. I gave this talk in March of 2024, and I'm recording it in February of 2025. I hope you enjoy it. So, pallasites are very unusual meteorites, and they're essentially composed of two things. One is these beautiful honey-colored olivine crystals that are swimming in a sea of iron, nickel, metal, and they're beautiful because when they're lit from the front, the metal shines, and when they're lit from the back, you see the light coming through the olivine. So the combination is quite spectacular. So a lot of people enjoy pallasites as pieces of jewelry. Here we've got a little necklace. Here's a ring, bracelet, little spheres. I'm not sure what people do with those, but people enjoy these meteorites as jewelry. Now, I presented this talk to the Mineralogical Association of Dallas, and so the question occurred, why wasn't I giving that to the Meteoritical Association of Dallas? And that's because there is no Meteoritical Association of Dallas. And you might say, well, why is there no Meteoritical Association of Dallas? And the answer is because most meteorites are not very good looking. Here we're looking at some of the meteorites we enjoy, which are okay, they're all right. But then on the right, it's competing with something like that, which is just a very beautiful mineral. So it's quite natural that a lot of people like pretty minerals, but most people don't care that much about meteorites. All right, so let's go over a few meteorite basics before we get into the details of pallasites. So meteorites are fragments of asteroids. They're not from Earth. They land on Earth. There have been about 160 observed falls of meteorites in the United States where people have gone out and collected the material that fell. And the first was in Weston, Connecticut in 1807. And the last one, as of a year ago, was in El Sauz, Texas. And on average, that's about one and a third meteorite falls in the U.S. per year. Now, there's about 73,700 meteorites that are found in the meteoritical database, an online database. And most of these are not falls, but these are things that people found in the course of, just going, oh, that's not a normal rock, and then looking at it and finding out, oh, it must be a meteorite. So there's quite a few of them, and there's more being found all the time. There's about 600,000 asteroids, and many of them, these are large ones, and there's many, many smaller bodies out there. And one of the things that scientists want to know is which meteorites came from which asteroids. And we call these parent bodies. And we'll talk more about this towards the end of the lecture. And right now, it looks like pallasites originate from at least 6 distinct parent bodies. Meteorites come from the asteroid belt, and the asteroids comprise a variety of small bodies. These are what we were calling parent bodies that never formed into a single planet. And it's estimated that these contain, a few million asteroids larger than 1 kilometer and many, many more smaller ones. And there's little impacts between these that knock off pieces, and some of them are sent towards Earth where they're collected. So they are quite interesting, very exotic, but why are they mostly not beautiful like many minerals on Earth? Get back into that. So it's interesting where we get our meteorites. There's two groups of people that are interested in meteorites. One is scientists, and the other are collectors. Now, collectors pay money for meteorites, and they get most of these now are coming from Northwest Africa. Whereas scientists don't pay for their meteorites, and they get most of them from Antarctica. So, again, meteorites mostly don't have beautiful minerals, with the possible exception of pallasites, the topic of our talk. So why is that? I asked ChatGPT how minerals on Earth form, and it said there's 6 ways. There's crystallization from magma, there's precipitation from a solution, there's metamorphism, there's hydrothermal processes, there's biological processes, and there's volcanic activity. I would add a seventh and an eighth. There's oxidation and there's evaporation. Then we'll talk a little bit more about these. So we can talk about the mineral forming processes on the Earth versus the ones on asteroids. So, as we said, on Earth we have crystallization from magma, precipitation from solution, metamorphism, hydrothermal process, biological, volcanic activity, oxidation, evaporation. We have all those processes on Earth. On asteroids, though, we only have crystallization from magma, some metamorphism, a little bit of hydrothermal, a little bit of volcanic. So there's only half as many ways of making minerals on asteroids as there is on Earth. And also, the processes on Earth have been going on for about 4 billion years. And these have been concentrating mineral forming elements increasingly in places where minerals form. Whereas, in contrast, the mineral forming processes on asteroids ended within a few million years when the solar system formed 4.56 billion years ago. So it hasn't had nearly as much of an evolution as Earth minerals. All right, so just to give us a little bit of insight into these asteroids, here are the four biggest ones: Ceres on the left, Vesta second, Pallas next to that, and Hygeia is the fourth largest. Now, it's funny, Pallas is not the source of pallasites, completely unrelated. They're named after a German naturalist, Peter Pallas, who lived mostly in the 18th century, a little bit in the 19th, who studied a specimen that was found in Siberia. So let's talk a little bit about the two main types of meteorites. There are undifferentiated and there are differentiated meteorites. This is the first order subdivision of meteorites. So undifferentiated bodies are ones that never melted, and ones that melted are called differentiated. So why did some asteroids melt and other ones didn't? It's got to do with a number of things. Size is a big part of that. But we don't really need to go into why some differentiated and some didn't. But the point is they did. So here we're looking at kind of the sequence of events that scientists think happened to make not only asteroids, but also the Earth. We can imagine this is the Earth. So we get different types of asteroid and meteorite types. So here is just a clump of undifferentiated material. That's what we call our chondritic stony meteorites. These are most common of the meteorites. They're not particularly attractive. They're scientifically very interesting. Then we get ones that come from a differentiated body, and the body can differentiate into a core, a mantle, and a crust like the Earth. And we think these iron meteorites that are perhaps the most famous meteorites, they come from the core of one of these parent bodies. And then there are some that differentiated bodies that look like they come from the mantle of the body. And then pallasites, we think, come from very close to the core mantle boundary in here. So these are pallasites are differentiated meteorites, and we think they come from that region. So 86% of all meteorites are chondrites, that is, they're undifferentiated, whereas only about 14% of meteorites are differentiated. About 5% of them are irons, like this guy, and 9% of them are sort of stony achondrites, like this one, and less than 0.5% of all meteorites are pallasites. So among meteorites, they're pretty rare. So back we go. These are the asteroids again, and we can talk about whether they're differentiated or undifferentiated. And we've worked this out from looking at the light they reflect, and Ceres and Vesta are both differentiated bodies, whereas Pallas and Hygeia are both undifferentiated. So how do we get this material that becomes asteroids and planets and these things? Well, we start the solar system, and the solar system started about 4.56 billion years ago when there was a gigantic gas cloud that condensed. It was hot at first, and as it condensed, it started spinning and started flattening into this disk, sort of looks like a pizza in here, and with most of the mass at the middle. This is called a protoplanetary disk, and most of that material in the middle went into our sun. And then slowly, the material in this protoplanetary disk um, collides and starts to make planets, and eventually we end up with what we have today, which is, the sun in the middle, Mercury, Venus, Earth, Mars, the asteroids, and then out here are Jupiter. So this is the sequence that scientists think happened 4.56 billion years ago to make the solar system. So this first 1 or 2 million years of our solar system history, the protoplanetary disk cooled and the hot gas condensed to a wide range of solids, silicate minerals, iron, nickel, metal, ices, and organic matter. And these all mixed together to make what we call chondritic meteorites. So here we've got a very famous chondritic meteorite called Allende. And if we look close up in a microscope, so that's 1 centimeter or about a half an inch, we see all of these little things that almost look like, grains in a sediment. And one of the interesting things in there are these CAIs. These are calcium aluminum rich inclusions, which are thought to be the first thing that condensed from the early solar system. And then also we have these roundish things, which are called chondrules, which are also interesting little melt droplets that somehow got incorporated in these undifferentiated meteorites. So we've been starting to send things to some of these undifferentiated bodies. This is one we sent. NASA sent a spacecraft called OSIRIS-REx, which sampled this body, which is only like, a half a kilometer across. So that's like 5 football fields across. And you can see it looks like just a big rubble pile. And that's what they call these things. And it came back and brought some material back in 2023. And this is what it looks like. It's this black stuff. It looks like charcoal, but these are in fact chondritic material. And now you can see that these are scientifically very interesting because they're coming from another body from outer space, but they're not very pretty, right? You wouldn't show a lump of charcoal as something that's pretty. But anyway, these are dark because they contain a lot of carbon. Now, this is one that we have in our collection at UT Dallas. So we've got a small collection of meteorites we use to teach meteorites to UTD students. And this is a carbonaceous chondrite, one of these undifferentiated meteorites. You can see the chondrules and some of these funny looking calcium aluminum inclusions in there. And it's dark matrix. This is what's that? That's about 5 inches across. It's a beautiful little specimen that our students really enjoy playing with. All right, so as we alluded to earlier, Earth and the other large bodies, they tend to melt and then they separate their layers by density. Iron, nickel is very dense and it will sink to the center of the planet and make an iron nickel core. Earth's core has got an inner and outer core. We don't need to go into that. And then that's surrounded by the mantle. And then on top of that is the crust where we live and where the oceans are. And so that's the structure of the Earth. And for that matter, any of these differentiated bodies is going to have a structure like that. So pallasites is coming from some area right around in here, very close to the core mantle boundary, but in a much smaller body than the Earth. So these are samples from an asteroid called Vesta. This is Vesta. We looked at it. It's the second largest of the asteroids, about 500 kilometers across. And we've got samples of its mantle, these things called diogenites, and we've got samples of its crust. That's what we call these eucrites. And then we've got some samples of the regolith, the sort of broken up material on its surface. Those are called howardites. So these are the HED meteorites, and this is one of the parent bodies for these meteorites that scientists have worked out. Now, iron meteorites are from the core of these differentiated asteroids. So here I am at the Smithsonian in 2022 looking at a very nice iron meteorite behind me. And this is one we have in our collection. This characteristic Widmanstätten pattern of iron meteorites is characteristic, not of all of them, but of many of them. And you can see a little bit of rust in here. That's what this stuff is. But this thing here is a different mineral called troilite, which is iron sulfur mixture, separate kind of a phase. But this is very, when you pick up an iron meteorite, wow, that's heavy. All right. So this is a sketch of scientist by the name of Ernst Caldini. Is a German physicist and musician in the 18th century and 19th century. And he wrote, if one were to write a geological Alice in Wonderland and try to think of the most handsome and yet improbable specimens, Pallasite meteorites would be strong contenders. And their unusual character and beauty may be the reason they were the first materials recognized and accepted by scientists, at least Caldini, in 1794. And this was about 10 years ahead of the scientific community, accepting that it was possible for rocks to sometimes fall from the sky. So Busick in 1977 said, pallasites contain only two major phases or minerals, olivine and iron nickel metal. These are very physically and geochemically different, and it's surprising that they're together. And the reason that it's surprising they're together is because they have very different densities, such that a physical separation of lighter olivine from denser iron nickel metal would be predicted. Yet there's lots of olivine in that metal, like cherries in a pie, and its occurrence there is really hard to understand unless the metal was molten at the time it formed. So pallasites give us a unique sample of the deep interior of a solar system body that has undergone extensive fractionation as well as a complex geologic history. So let's talk a little bit about the two components. There's olivine, and here we have a couple of samples of olivine that are in collectors' possession. And this olivine is a solid solution between magnesium silicate, which is called forsterite, and iron silicate, which is called phthalate. And for shorthand, we can call forsterite FO, and for phthalate, we can call it FA. So the shorthand for olivine composition is given by the percent of forsterite, which is written as FO with that subscript at the numbers. So pure magnesium olivine would be FO100. And a 50-50 mixture of forsterite and phthalate would be FO50. So Earth's mantle is dominated by olivine with a content of FO90. And the olivine in pallasites is typically FO89 to FO80. And one of the interesting things is the more iron that there is in an olivine, the darker green is its color. That's what we're seeing here. So pallasites are rare types of meteorites, as we've said earlier. There's only 61 are known, including 10 from Antarctica, with 4 being observed falls. And the following 4 falls are in chronological order. There was one in Sicily in 1826, and there was only about an ounce and a half of that was preserved. There's Zycho, there about 330 grams were found after a fireball in 1898. And then in Russia, there was a large mass that fell in 99 pounds. And this collection belongs to Finland. And the main mass of it is at the University of Helsinki. And then Omlon, another place in Russia, a reindeer breeder observed the fall in 1981 and found 250 kilogram meteorites 2 years later. So those are the four that are confirmed Pallasite falls. The rest of these are finds, including the one that we have in our possession. So pallasites are essentially composed of olivine crystals swimming in iron nickel metal, as we said. And so here is a nice photograph of it. And here is, if it came from Earth, which it didn't, this would be the location it came from. So we've been thinking for some time that pallasites are samples of the core mantle transition zone of some kind of a differentiated asteroid. All right, so how did they form? So this is one idea that there was some kind of an impact of two differentiated bodies, so that one of them hit the other one, and the core of the one sort of interacted with the mantle of the other one, and so you get that you would expect this kind of a mixture in here. So maybe this is what we're seeing. This is a pallasite, and this kind of looks like a mechanical mixture of stuff from the mantle, the olivine rich mantle of a body mixing with the iron from a core. So maybe that's something like that formed in there. And this is an example. This is a semchan. This is a pallasite that's mostly iron, but has a bunch of little heterogeneous parts that have got olivine in it. Maybe this kind of a pallasite represents what might happen as a result of impact of two bodies and mixing of the core of one with the mantle of another. Here's another example from Semchan. So you can see this is very rich in olivines over here and over here, and then this middle part is almost pure iron nickel metal. So, when you see something like that, you would say, yeah, that kind of looks like how it formed. You could see that this kind of a structure would be forming in something like that region. So, another view of Semchan. But many of these pallasites don't look like this kind of mixing between an olivine rich part and liquid metal. They look more like the kind of things that would occur if you were making cookies and just putting little olivines in the middle of dough made out of iron nickel metal. Like, look at that. It's hard to see that structure as coming from a collision and a mechanical mixture of iron-rich metal and olivines. They're very homogeneously distributed through here. This is Saricho, which is a different pallasite. This is a different part of Semchan. It's very sort of homogeneous distribution of the olivines separated by iron nickel metal. Here's another one of Semchan. This is Esquel, which also looks like, for some reason you've got these little chocolate chips of olivine in the iron nickel dough. And then this is Imilac, very beautiful one that was on the cover, the first slide we showed. This is Bonham. This is, olivines and iron nickel metal separating them. So That's what we know about pallasites. Now, one of the interesting things that's happening right now is we have sent a, space probe to asteroid 16 Psyche, and it is an M-class asteroid. That means it seems to be metallic, and some scientists think that this might be a source of pallasites. So that launch happened in October of 2023. And by August of 2029, the spacecraft will begin to orbit the asteroid. And to date, this will be the only metal class asteroid ever to be explored. So stay tuned. We're going to have some interesting results, whether or not Psyche is a Pallasite meteorite. So that's the end of my show, and thank you very much for listening.